In this video, we're going to cover combinational logic circuits performing arithmetic operations. In the previous video, we have seen logical functions implemented by combinational logical circuits. Now we will attempt to put together new circuits which will use logical functions to implement arithmetic operations such as subtractions and additions. Later on, we can also speak about possibilities for multiplication and division. Binary number addition for 1-bit size inputs can be represented by this truth table. So let's just study possible outcomes, and in general there are 4 possibilities for resulting sum and carry. You can see that 0 plus 0 equals 0, and therefore if our sum, the result of this operation, is also a 1-bit value, then it's not a problem to represent this result. Likewise, we can see that 0 plus 1 and 1 plus 0 results in 1, so we still can successfully represent results in the sum column. At the same time, when we add 1 plus 1, the result is decimal 2 or binary 10, and of course this extra digit that is generated by 1 plus 1 has to be represented by an additional bit. We will call it a carry bit, and you can see that in our first 3 cases we had it set being 0, and only when we add 1 plus 1 the carry is also set to 1. A quick look at the carry and sum columns in our truth table should be obvious that carry is an AND function on our inputs, and the sum is an exclusive OR. This simple circuit implements this truth table. Therefore, we can view it as a combination of 2 gates, exclusive OR, and the AND gate, which implement the desired results. The circuit that we've seen on the previous slide is commonly known as half adder, and as its name suggests, it has 2 inputs, it has a sum result and 1 carry out. However, it does not provide any possibility to connect such devices together in order to be able to produce multi-bit addition. So once again, I'm just jumping back here, and what we can indicate that if we do have a carry and this is going to be a multi-bit addition, we have an extra output from our device, but if we wanted to connect it sequentially to another such device, another adder, we are missing an input that otherwise be needed to make such connection. And this is why this logic gate circuit that we have here on this page is known as half adder. So it's just half of the job done. And as this discussion suggests, we actually need 3 inputs to make the adder circuit useful in multi-bit situation. Such circuit is called a full adder. So with the full adder, we need to extend our truth table by adding another column of data, and it's called carry in. So we have 2 inputs, A and B, and also carry in signal that potentially could be coming from another full adder. So on the left hand side of this table we have 3 inputs, and on the right hand side of this table we have two outputs. We simply implement this truth table by adding three 1-bit inputs, A, B, and carry in, and record a binary result by placing two of the resulting bits in these two columns. The sum is the lower bit and the carry out is the higher bit. As you can see, 0 plus 0 plus 0 is 0, and then we go to 1, and then we continue with adding it, and we continue with the 1, and so forth. And we initially fill in all the possibilities, like for instance where we have two 1s and a 0, the result is decimal 2, which is binary 1, 0, binary 10. And in the last row of this table, we have 1 plus 1 plus 1, which is decimal 3, which of course we can record as binary 11. This circuit implements a full adder example that we had on the previous page, and it's perhaps an efficient way of doing this. However, we're going to try to attempt to use a more primitive, which will look more like a decoder of these three potential inputs to our full adder. So this is the version of the circuit which makes it a different implementation. So it combines these three inputs with the carry and the two input bits, and then we have a decoder over here which basically suggests that whenever there is a certain unique combination of these inputs, only one of these outputs will signal 1, all other outputs will be set to 0. So this is achieved by using 3 inverters, 2 inverters in different combinations, also 1 inverter, and therefore as we change the values of A, B, and C, all 8 actually unique combinations will be assembled into 1, 2, 3, 4, 5, 6, 7, and 8 potential variable answers which will decode the unique combination. In other words, once again, when there is a certain combination, like for instance if our inputs are all set to 1, okay, so all 3 inputs are set to 1, as you can see all 3 of them are being supplied to this gate, so this will be 1, 1, and 1, and this 3 input AND gate of course will result in producing a signal which will go to both OR gates, also 4 input OR gates, and both carry and the sum will be in this case set to 1. So of course the result will be 1, 1, which is binary 3. 1 plus 1 plus 1 is binary 11, which is decimal 3. So this is the nature of something that we will refer to in the future as a programmable logic array, but its implementation is less sophisticated than the one that we saw on the previous slide, because it's using less gates, because it's using a more optimized version of this combinational logic circuit. But in this case, we just produce essentially a closed box device which we can program by supplying certain number of inputs and certain number of outputs, and encoding our truth table into all of the connections in this type of device. So of course we're interested in a multi-bit version of adder, and if we have two numbers that are being supplied by two inputs A and B, so for instance if we have an input A with bits with 4 bits, and another input B also with 4 bits. We would then supply these two inputs into a chain of these full adder circuits, which are shown here as these closed boxes, and essentially connect all A inputs to the corresponding A bits over here, and likewise the corresponding bits of the B signal, which we also have here available, will be connected to the corresponding B inputs, and then we can expect that if we chain together these full adders, we should be expecting to get the correct sum result in these outputs indicated by sum. As you can see, to make carryover work properly, what we do is that if we add inputs and the outcome is such that both are set to 1, so of course 1 plus 1 is 2, and then if the initial carry is 0, the sum will be 0, but the carryover is going to be 1. So the carryover is going to be supplied to the next closed box circuit, next full adder, which will then combine this carryover with the inputs from the corresponding bits of A and B, and this should again work to produce a certain sum and, if necessary, a carryover to the next device. So this each of these boxes deals with individual bits in our inputs. So we're expecting here once again that the two numbers A and B, two binary numbers that we're going to be adding by such a 4-bit full adder device, are going to be consisting of 4 bits. So these are designed for 4-bit inputs, so the two 4-bit inputs can be added, and we're expecting to generate a sum over here, so which is also a 4-bit output